Let's say you're playing squash, hitting the ball against the wall in front of you. And as your partner expects the ball to bounce back to him so he can hit it, no ball comes. The ball has disappeared. Behind the wall is a second squash court, and the players in that court find that they are playing with 2 balls. Your ball went through the wall somehow. You look for holes in the wall, but find none. What happened here? This phenomenon is known as quantum tunneling. In quantum mechanics, when a quantum object like an electron encounters an energy barrier, like a wall, there is a non-zero chance that will end up on the other side of the wall. This is possible because you have to remember that quantum objects are defined by a wave function, and the wave function extends to all of space-time. This means that it extends not only in your court, but also into the wall and outside the wall into the other court. And the smaller the energy barrier, that is, the thinner and lower the wall, the greater the probability that it will end up on the other side.
I made a subatomic particle detector.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particular is happening. Well, this is really one of the great phenomena in 20th century physics.
The liquid helium had turned into a superfluid which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
This creeping film is a variety of superflow. It is difficult to make the film itself directly visible to you.
Okay, what you just saw is called a superfluid, and there's nothing normal about them. If we take helium, for example, and cool it down to 2.17 Kelvin, that's very cold, by the way. It enters an exotic state of matter called a superfluid. First of all, superfluids have zero viscosity, meaning they have no friction in them. So unlike a normal liquid, if you were to stir a superfluid, it would theoretically keep going on forever in these quantum vortexes. Because superfluid helium has zero viscosity, it's able to form what's known as a Rollin film. This is a 30 nanometer thick creeping film that's able to defy gravity and move up the sides of any vessel you try to contain it within. And that's why in the video you saw initially, those drops are forming below it, because the helium is actually rising around the container edges and collecting at the bottom.
Water has many amazing properties. Its surface tension enables things like bugs to walk across it without sinking. Water also becomes less dense as it freezes, which is why during winter, lakes freeze from the top down and life persists at the bottom. Now, scientists have observed a bizarre quantum mechanical trick in the smallest possible droplet of water. Water's ability to form hydrogen bonds is behind most of its extraordinary feats. Water molecules are always bonding with one another, switching partners like dancers. In order to study these bonds, researchers performed low-temperature experiments on a cluster containing only 6 molecules, the smallest droplet that will form a 3D shape. By distinguishing the individual water molecules in the cluster, they observed a surprising result. 2 different molecules in the cluster move in sync, breaking 2 different hydrogen bonds at the same time. The rotating molecules mesh like gears in a watch. Here's where the weirdness of quantum mechanics comes in. At the low temperatures used in this experiment, the molecules don't jiggle with enough energy to even break 1 hydrogen bond. There is an energy barrier between the 2 configurations that's too high to scale. But thanks to quantum uncertainty, there's still a chance that the cluster will simply pop through that energy barrier, a bit like walking through a wall. That weird trick is known as quantum tunneling. This unexpected cog-like motion in the tiniest droplet shows once again how plain old water continues to serve up scientific surprises.
Scientists tried to figure this out by shooting 1 photon at a time. If it was a particle like a grain of sand, we would expect it to go through one slit or the other and make a spot on the screen, but this is not what happened. The photon seems to randomly make a spot somewhere on the screen. And if we shoot thousands of photons one at a time, we see the photons make an interference pattern. The photons, even though they were shot one at a time, so had no chance to interfere with each other, seem to make an interference pattern as if they interfered. Could it be that each photon somehow splits into 2 and interferes with itself? To test whether that's what's happening, we can put a detector near one of the slits to see if the photon goes through that slit or not. And sure enough, the detector tells us that the photon went through only one or the other of the slits. What this experiment suggests is that photons and quantum objects show characteristics of both particles and waves, the wave-particle duality of matter.